Imagine storing millions of tons of carbon dioxide underground to help combat climate change. However, what if the very process designed to reduce emissions gradually become less effective because tiny salt crystals begin to clog to the reservoir pores? My name is Hazleen Shahira binti Sulaiman, currently in my final year second semester, pursuing a Bachelor of Petroleum Engineering with honours at Universiti Teknologi PETRONAS under supervision of Dr. Mazuin, binti Jasamai. Today I will present my research entitled Impacts of Brine Composition on Salt Precipitation Morphology and Mineral Alteration in Carbonate Rock during CO₂ storage. Geological carbon capture and storage, or CCS, is widely recognized as one of the most promising technologies for reducing atmospheric CO₂ emissions and supporting global climate goals. According to Fento et al. 2025, geological CO₂ storage is expected to play a critical role in achieving net zero emissions mitigating climate change. In this process, captured CO₂ is injected into depleted reservoirs deep underground for long-term storage. However, when dry supercritical CO₂ enters a carbonate reservoir saturated with brine, water begins to evaporate. As water evaporates, dissolved salts become concentrated and eventually precipitate as solid crystals. These salt crystals can accumulate within pore space, and pore throats can cause pore blockage, which can reduce permeability and ultimately leading to injectivity decline. Although salt precipitation is widely recognized, the influence of different brine composition on salt crystal morphology and mineral alteration remains poorly understood, so this knowledge gap limits our ability to accurately predict formation damage and optimize CO₂ storage strategies. Therefore, this study aims to investigate how different brine composition and influence salt precipitation and mineral alteration during CO₂ storage. Specifically, this research has three objectives. First is to determine how different brine compositions influence the size, shape, distribution, and aggregation of salt crystal formed after CO₂ exposure. Second, this research is to analyze the effect of pore geometry on salt precipitation before and after CO₂ brine interaction. Lastly is to examine mineral alteration mechanisms in carbonate rocks exposed to different brine composition. So by understanding this mechanism, we can better predict injectivity decline and also improve long-term storage performance. So to achieve this objective, limestone samples representing Central Laconia carbonate reservoirs were used. So 4 chloride-based brines were prepared, which are NaCl, KCl, MgCl2, and also CaCl2. Each brine was prepared at a salinity of 20%. So the sample was saturated with brine and exposed to CO₂ under simulated reservoir conditions, which are 900 psi pressure, 50 degrees Celsius temperature, and also 14 days exposure period. Following exposure, there are several analytical techniques were employed. FISEM was used to visualize salt crystal morphology and pore scale distribution. EDS was used to determine elemental composition and elemental mapping. Lastly, XRD was used to identify mineralogical alteration and newly formed mineral phases. Together, these techniques provide a comprehensive understanding of salt precipitation behavior and rock alteration mechanisms. Based on previous literature and expected outcomes of this study, different brine compositions are anticipated to produce distinct crystal morphologies. So according to Zhang et al. 2025, salt precipitation patterns vary significantly depending on pore structure and also brine chemistry, directly influencing the extent of pore blockage and also the formation damage. So NaCl is expected to form cubic crystal that cause moderate pore blockage. KCl may produce cubic prismatic crystal with greater flow restriction. MgCl2 is expected to generate needle-like or aquilar, leading to the more severe pore blockage and stronger carbonate dissolution. In contrast, calcium chlorides, which is CaCl2, may form plate-like structures that create a protective layer and reduce mineral dissolution, as is as is illustrated in the conceptual model, salt precipitation is expected to be more severe near the wellbore where brine evaporation is highest. So further away from the wellbore, lower CO2 concentration reduce precipitation intensity and help preserve more conductivity. So this research directly contribute to SDG 13 and also SDG 7, which are climate action by enhancing the effectiveness of geological carbon storage, so technologies that reduce greenhouse emission, and also affordable and clean energy by enabling safer and more sustainable deployment of low carbon energy solution. So in conclusion, brine composition play a critical role in controlling salt precipitation morphology and mineral alteration during CO2 storage. So by improving our understanding of CO2 brine rock interaction, this research contribute to safer, more efficient and more reliable geological carbon storage system. Thank you for your time. That's all my presentation.